In the last lecture, I was just showing you the course outline, and as part of that, what I did not specifically mention are the learning outcomes for the course itself. So, what are these? First of all, we are trying to identify the fundamental principles of photonics and light matter interactions. Then we are going to try to develop an ability to formulate problems related to photonics, photonic structures, processes, and analyze them. And finally, we are going to try to identify processes that help to manipulate the fundamental properties of light. And of course, that is what we saw in the last lecture. We were trying to identify 3 modules. So, those 3 modules are consistent with the learning objectives of this course. So, let us go back and have a quick recap of where we were yesterday. We were starting with a general statement as to why we should be interested in photonics. We were trying to list down a number of applications where photonics play a central role, and then we went on to say, when you look at how we try to analyze the photonics processes, we start with ray optics, where as Fermat mentioned, light travels in straight lines. It is a very simple concept, and then we say, okay, ray optics cannot explain everything, some of which we are going to actually look into a little more detail today. So, concepts like wavelength and phase of light is not something that you can capture in ray optics. So, you necessarily have to go into wave optics, and then of course, even the wave optics is not sufficient to explain concepts that are based on polarization of light. So, to capture those, we go to electromagnetic optics, which started with Maxwell making his declaration around the mid 1800s that light travels as electromagnetic waves. And then I got this wrong, the year wrong. Planck actually came up with this paper in 1900 that essentially was saying that light emission and absorption are quantized, and then that was followed by Einstein's observation that light itself comprised of quanta of energy, which later on was defined as photons. So, as I was mentioning yesterday, we are starting with ray optics, examples in ray optics, and then we will proceed to looking at examples with wave optics, and beyond that we will get on to electromagnetic optics and eventually to quantum optics. Okay, that is what we are going to progress. And as far as wave optics, ray optics examples are concerned, we took the example of endoscopy, where we said we need an optical probe for doing endoscopy, and how do we go about designing this optical probe. And designing this optical probe, we said it's fairly simple. We just need to know the law of reflection and law of refraction. So, we were just revising that a little bit, and then we went on to define this structure wherein you have an material with refractive index N1, which is surrounded by another material with refractive index N2, and then we said we could have total internal reflection at the interface if the angle at which the light ray hits the interface is greater than the critical angle, right. And then we said we could have reflection, and then if you have a consistent structure where you have this interface between N1 and N2, and those two interfaces are parallel to each other, then we will have consistent guiding of light within this structure. So let's go on and look at this in little more detail. What we are typically interested as far as the endoscope is concerned is you have a structure, let us say a waveguide structure, because we are saying that we are actually guiding a light guiding structure, and what is the maximum cone of angles that we can pick up using this structure. So, I have tried to lay out in this picture, wherein what we need to do is take care of this condition, that is the incident angle being greater than the critical angle as far as this interface between N1 and N2 is concerned. And then if you trace it back and you see what that means as far as the launch of light into this structure is concerned, so you will have to essentially look at what is happening at this interface over here. So typically the outside medium is air, and then you are going into a glass material. So let us say with a refractive index N1. Okay, you can apply Snell's law over here, and what we are actually trying to find out is the maximum angle which can be supported at this interface, such that the light is guided through the structure, right. So the limiting condition for such a guiding is theta 1 equal to theta c. Why? Because we clearly need to have this angle satisfied. We need to have an incident angle greater than theta c for light to be guided. And if you look at the Snell's law at this particular interface, for very small angles of theta naught, for example, the limiting case is where theta naught is going straight down this dotted line over here. So the light ray is going straight down, there is no problem, light will go straight through this waveguide. And as you increase theta naught, okay, you get to a point where your angle at this interface is going to become smaller and smaller, okay. And if the angle theta 1, if it is becoming less than theta c, then there is no guiding of light, right. So the limiting condition would be theta 1 equal to theta c. So if I am able to find the corresponding angle theta naught, then I would say that anything within that cone of angles defined by theta naught is going to be guided in this structure. Anything outside of theta naught is going to be such that theta 1 becomes less than theta c, then it is not guided by this structure, okay. So these cone of angles that is allowing light to be guided in this structure is called numerical aperture of this endoscope. So what we are actually trying to get to is what is the numerical aperture of this waveguide, of this light guide, right. We have not started talking about waves, so we will just keep it as a light guide, okay. So to do that, I go and apply Snell's law at this interface over here, at that input interface. So I write n naught sine theta naught equals to n1 sine of this angle, but the refracted angle, we would realize that if this is theta c, then this angle is theta c, that is the opposite angle, right, and this has to be pi by 2 minus theta c, right. So I would just say on this side it has to be n1 sine of pi by 2 minus theta c, that we know corresponds to cos theta c, right. and cos theta c can be written in terms of sin theta c as root of 1 minus sin square theta c. And what we saw in the last lecture is that sin theta c is given by n2 divided by n1. So, I substitute that over here. Okay. So, you get n1 root of 1 minus n2 over n1 the whole square. Okay. And if I take the common if I take n1 in common, then I get this simple expression which says sin theta naught, especially since we are considering n naught corresponds to air, n naught equals to 1, then sin theta naught is root of n1 square minus n2 square. Okay. So, this is a very simple picture that is enabled by ray optics, right. We did not do anything other than law of reflection, law of refraction here, and we came up with this sort of formulation. Okay. So, and of course, what this tells you is that you want a very large numerical aperture. What should you have? What do you want from an endoscope? Normally you want a very large field of view, so you can see things on either side over a fairly long angular spread, right. So, how is that enabled as far as the structure is concerned? N1 has to be much greater than N2. So, if you have a large index contrast between the two media, right, you can essentially support a large numerical aperture. So, how is this realized? You basically have a cylindrical wire, okay, with refractive index N1, let us say it is made of glass, and you coat it with a polymer, right, with a much lower refractive index. So, glass, you say refractive index of 1.5, and that is actually a very loose definition, I should tell you, because that is what you hear in high school textbooks, that glass is refractive index of 1.5, water is refractive index of 1.33 and so on. But you have to take that with a pinch of salt, because in reality that refractive index is actually dependent on wavelength. Remember this thing about how do you form a rainbow, right? How do you get a rainbow naturally? In sunlight consisting of different colors is going through this raindrop, which can be modeled as a prism made of water. Water essentially has a different refractive index, slightly different refractive index for each of those colors. So, when you apply Snell's law, each of those colors separate out in terms of the angle of refraction, and that is essentially what you see as dispersion, which causes the rainbow, right. So, in general, that's a key thought that you should have in mind, that the refractive index of material, or in more basic terms, is the permittivity of the material, the response, the dielectric response of a material is frequency dependent or wavelength dependent, or in layman's language color dependent. So, it depends on the color as to what is the refractive index. But nevertheless, if you say that you have a glass central structure surrounded by a polymer structure which is of much lower refractive index, then you can make an endoscope with a very large numerical aperture, with a very large field of view. Okay. So, that is what goes into the design of an endoscope, the optical probe for an endoscope, which we just now explained using ray optics principles. So, ray optics principles in general go a long way. With ray optics, we just saw how to design an endoscope. We can explain dispersion in prism, right. you can explain, for example, you can actually do optical system design, right. So, which is consisting of multiple lenses, multiple mirrors and so on. You can do all that optical system design, and you can go all the way up to designing a telescope. A telescope is nothing but a series of lens elements that are put together. You can go all the way up to designing the Hubble telescope. You know what a Hubble telescope is? This telescope that people put in space, right, which is capturing images of the galaxy, deep out in space. So, something as sophisticated as that could actually be the basic design of the telescope can be achieved by just ray optics principles. That is the power of considering light as something that just travels in straight lines, and you are able to deal with how it propagates through multiple interfaces. Okay, so let us just look at how do you go about designing something. I do not have time to go through this in very high level of detail, but let me just give you a feel for how people do this complex lens systems, optical systems. How do they use ray optics to see how light propagates through these systems, right. So, let us say you have an optical system. One of the key things that you define is an optical axis, basically the central line that joins all the optics within that system. So, let us say it consists of a lens here, another lens over here. Let us say those two are what I call biconvex lenses, and this is actually a biconcave lens, and maybe another lens over here, right. So, if you want to analyze a system like this, what you want to know effectively is, if I consider a plane over here and a plane over here, okay, I want to look at a ray that is incident on this plane, okay. What happens to the ray as it propagates through the system, and specifically I am interested in how the ray comes out of that optical system, right. That is a typical problem that we look at. So, what you could do is define the distance from the optical axis y1, and let us say it is making an angle theta 1 with respect to the optical axis, and over here you go to y2, and that is exiting the system with an angle theta 2. Okay. So, the idea is, if you are talking about a linear homogeneous system, that is within that lens it is all homogeneous, or within the propagation between the lenses it is all homogeneous medium. If you consider medium like this, you can actually write the output y2, okay, in terms of the input parameters. Basically, you say it has some dependence on where the ray is entering the system, so y1, and it has got some dependence on what angle the ray is entering the system, theta 1. Similarly, if you want to find theta 2, that again has a linear dependence on what's how it's coming in. So, you have c times y1 plus d times theta 1, okay, to the point that you can write this in matrix form. Y2 theta 2 is what you want to find out, y1 theta 1 is the input, and then you have this matrix ABCD which defines this optical system. Okay. So, if you can model the propagation of a light ray within each section of this optical system through each surface of this optical system, then essentially let us say this is what you call as the ray matrix, and the ray matrix is actually going through multiple sections, multiple surfaces, and each one of those has its own ABCD matrix. Okay. So, you say, let us say there are n such occurrences, mn, mn minus 1 and so on up to m1. This would be the effective matrix that defines this entire thing. Let us just take one quick example and see how this works. So, and I will take a very simple example in the interest of time. So, let us say I just have a ray that is going straight through this system. Okay. I want to define how the propagation happens through free space, okay, without any elements coming to the picture. So, how would the ABCD matrix look for something like this? Okay. So, I can essentially write, so this is y1, this is y2, this is theta 1, this is theta 2. Okay. So, we know that theta 2 equals to theta 1, right, and what is y2? So, whatever this distance of propagation is, let us say that corresponds to d. So, you essentially say this is going to be given by y1 plus d times theta 1. Okay. So, this would correspond to, I just flipped it, but you know y2 goes up and theta 2 comes below that. So, the ABCD matrix corresponding to this is 1, A corresponds to value of 1, B corresponds to a value of d, that is the distance of propagation in this medium, C is 0, okay, that is a coefficient of y1 and that is 0, and d is 1. So, the ABCD matrix for a simple propagation through free space corresponds to this. So, you can do this for a lens as well, okay, and especially there is one approximation which becomes very handy in these sort of situations. This approximation is called the paraxial approximation, paraxial, right. So, it is something to do with axis. So, what does paraxial mean? It essentially means that we are considering rays to be having a very small angle with respect to the optical axis. Okay. So, in the paraxial approximation, if you write sin theta, when theta is small, what is the value of sin theta? Theta itself. So, it can be approximated as theta. So, how does that help? Because as you are propagating through this optical system, you are encountering surfaces, and at each surface you are applying Snell's law. Snell's law says sin n1 sin theta 1 equal to n2 sin theta 2, but you do not want to put all these sin cos things within this matrix. So, Snell's law will become n1 theta 1 equal to n2 theta 2 in the paraxial approximation. Okay. Then it is easy to form a corresponding matrix and then go through this thing. So, what is the disadvantage of this? Obviously, you cannot account for rays that are making a very large angle with respect to the optical axis. So, if you have a very large numerical aperture like what we were trying to do with the endoscope, we are trying to have a very large numerical aperture, that cannot be modeled here. But if you are talking about modeling a telescope is seeing something that is happening thousands and millions of kilometers away. Light coming from there is going to be fairly aligned to the optical axis of your telescope, right. So, paraxial approximation works very well if you are looking at really distant objects. Can you apply that for a microscope? Probably not, right. So, you are trying to magnify a small object and you have a very large spread of angles within that, and so it's not easy to apply that to a microscope. Okay. So, that just gives you a general thought of how far you can take ray optics. Okay. Any questions before we move on? Why is the? So all of these, once we put it in this form, all of these are linear transformations, right. So the entire system becomes a linear system, and we are considering homogeneous material. So yeah, we are taking essentially a linear response from the system. That is the basic assumption. Okay. So let us move on and move back to what we wanted to carry on with for the rest of today's lecture. Okay. And that actually takes us back to this tiny tidbit that I gave at the end of the last lecture. What did we do? What did I ask you to do? Right? There is one word to explain that. Right. So, diffraction of light is what is happening. So, what is diffraction? Now, whatever we have been saying so far, or whatever we have been seeing so far, is that when you have a large opening, you can use ray optics to see what is happening on the other side, right. And when I say large, what exactly do I mean? Large is how large? Very good. So, it is comparative to the wavelength of light. So, if you have an opening with let us say d as the dimension, that is far greater than the wavelength of light, right. So, you can explain everything by ray optics. But what happens if you have a very tiny aperture, very small aperture? So, in this case d approaches lambda. Okay. As d approaches lambda, there is very little light that is going through, but we are not worried about how much is the intensity of light. We are worried about characterizing the property of light beyond that point. And this is what Huygens did much earlier, several centuries ago. He actually said that light propagates through the structure as waves. Okay. So, his hypothesis at that particular point was that light propagates with waves very much like a pebble dropped in water, right. So, you see waves that are going out from the point where the pebble has gone through the water surface, And another example could be sound from a loudspeaker, right. So, you have this loudspeaker blaring out and you can hear that sound over a very wide region because sound is propagating as waves from that source and it's actually spreading around. So, ray optics breaks down, right, when you consider features that are comparable to the wavelength of light. Okay, that's a key thought that you want to carry on, right. Ray optics gets limited when it is actually having to deal with structures where the feature sizes are comparable to the wavelength of light. So, you have to jump over to wave optics and you need to understand how light propagates as waves. Okay. And any problem where you are dealing with propagation of waves, where does it start? Where would you start any formal problem which is dealing with waves, propagation of waves? The wave equation, right. So, what does the wave equation tell you? Basically, del square of u, let us say u corresponds to the description of the light wave, okay. Del square u minus 1 over c square is multiplied by dou square u over dou t square is equal to 0. That is your wave equation. Now, of course, you are familiar with this in a slightly different manner. A lot of you would have seen this in electromagnetics. In electromagnetics, what you would have seen is U is replaced by E or H, the electric or magnetic field, right. So, if you substitute U, instead of U you substitute E or H, you get the wave equation, which from Maxwell's equations, a couple of steps you get to the wave equation, right. So, that is the same format that we have. Okay. There is something, one approximation that you can take at this point in terms of finding a solution for the wave equation, and that approximation is associated with the general observation that when you look at waves, these waves are normally periodic in nature, right. So, you drop a pebble in water, you see these waves and those waves are essentially periodic in nature. So, you can actually go on to describing them as time periodic signals. And what is the advantage of looking at them as time periodic signals? If I am looking at the solution for u in terms of, let us say, Cartesian coordinates x, y, z and t, the time dependence, then this can be written as u of x, y, z, and then the time dependence comes out as e power j omega t, right. E power j omega t is basically cos omega t plus j sin omega t, right. So, it is basically representing a sinusoid, okay. So, we are saying it is basically a time periodic signal which corresponds to a sinusoid, and we represent it this way. What is the advantage of representing this way? If I want to take a derivative with respect to t, if I differentiate this with respect to t, then that will give me j omega, right, and rest of it is going to, the u is going to remain the same. And if I want to do a second derivative, which is what we are trying to do over here, right. If I want to do a second derivative, that is nothing but minus omega square, okay. So, I can substitute, instead of this second differential here, I can substitute with minus omega square, which gives me del square u plus some variable k, k square u equal to 0. So, this is my wave equation for a time periodic case, okay, where k is given by omega over c. Omega is nothing but the angular frequency. So, you can write it as 2 pi f over c, and c over f is what? C is the velocity of that electromagnetic wave, sorry, in this case this light wave, and f is the frequency. So, c over f would correspond to lambda. So, you can write k as 2 pi over lambda. So, what does that mean? Essentially, if I look at the solution of this, right, the solution of this, let us say this corresponds to a wave that is propagating in, let us say, the z direction, positive z direction, okay. Then the solution of this can be written as u of r, where r can be some any radial parameter, is given by a of r multiplied by e power minus j k z e power j omega t, okay. So, how do I get minus j k z? If you go back here, this del square is actually a Laplacian, okay. So, in Cartesian coordinates, this corresponds to dou square over dou x square plus dou square over dou y square plus dou square over dou z square, right. Now, if I say it is propagating along z and I say it is actually propagating with very little loss, okay, then the z propagation I can write it is only there is a accumulation of phase in that term, and that is what we get over here. So, if I actually look at this in the z direction, what I would find is, this is basically you are looking at u of r, what you would find is it is actually propagating in some, it is varying in some sinusoidal fashion, and this, from where it goes from 0 and goes to 0 again, what does that correspond to in space? Wavelength. And over the wavelength, how much phase does it accumulate? It accumulates a phase of 2 pi radians. So, effectively what we are saying is this term is representing the phase that the wave accumulates as it is propagating, okay. And this e power j omega t term is actually a fairly boring term. I mean, it's representing the time dependence, but it's actually a periodic wave. So, so that's not changing when it's going through material, right, linear material. So, we can choose to just consider the wave as a what is called a phasor. So, u can be considered as a phasor, which means that the representation is e power a multiplied by, it has got some amplitude a and e power j phi, okay, because we are interested in tracking the phase which actually is changing during the propagation of that light, okay. So, I can just represent this in a very simple form, in the phasor form, and u in general can be a complex quantity. So, you can represent plot the real part of u against the imaginary part of u. So, when I am plotting like this, what type of plot is this? It is a plot in the complex plane. What do we call this? We heard of a polar plot, right. So, you essentially have a polar plot where this is a phasor with an angle phi, and it's got a magnitude A. Okay, so you can represent this in terms of a phasor. And now if you want to define propagation, we know it's actually going through a sinusoid. So you can say that as it propagates, it accumulates phase, right, and it's basically going round and round in this phasor. So it basically goes around and it's repetitive, just indicating that it's actually a time periodic function, right. So now with this we can go ahead and explain what happens when two waves come together, which is what it's amazing. This experiment was done in 1801, as early as 1801. So this person Young, Thomas Young, did this experiment, right. Thomas Young did this experiment where he basically defined two slits, okay, which are separated by, let us say, a center to center separation corresponds to D, and then he was observing the propagation of light through this. So you have a wave that's incident on this aperture. So what happens? And these, each of those slits were quite small in sense it's approaching wavelength. So effectively what you expect is this goes on like this, and then similarly you have another wave like this. It's similar to in a bucket of water you drop two pebbles, both the pebbles hit the water at the same time, and you have these waves that are coming across, and then they add with each other at some point, right. So and they may cancel each other at some other point. So let us say this is our observation plane. So what do we see over here? So let us actually define an optical axis that goes through this, and what you see on this side is a fringe pattern like this, which goes to maximum and minimum alternatively, okay. So how do you explain this fringe pattern? Essentially, if you look at the total intensity over here, let us say that corresponds to I corresponds to, let us say the field is represented by U. So the magnitude of the field and square of that corresponds to I, but this is now represented by two different waves. One wave which is represented by U1 is A1 e power j phi 1, and another wave which is represented by U2 corresponding to A2 e power j phi 2, okay. So U is consisting of contributions from both those waves. So, u1 plus u2 and both are complex quantities, right. So, when you do this square, what you get is u1 square plus u2 square and then the beat terms between them. And since it is a complex quantity, what you will get is u1 u2 conjugate plus u1 conjugate u2, right. So, you substitute the respective expressions, the phasors for u1 and u2, what you get is this one u1 square is going to correspond to I1 intensity of wave 1, u2 square corresponding to I2 plus 2 root I1 I2 e power j phi 1 minus phi 2, because we are looking at the conjugate of u2, right. And similarly, the other term is going to be 2 root I1 I2 e power minus j phi 1 minus phi 2, right. So, those are going to be the two beat terms, and you can simplify that, and I am going to slide over here to do this. So, I can write my total intensity I now. So, it has got a common beat term root of 2 root I1 I2, and then you are adding these two terms e power j phi 1 minus phi 2 and its conjugate, right. So, when you add those two, what do you get? So, e power j theta is cos theta plus j sin theta, right. So, you are going to get, sorry, I made a mistake here. So, there is no 2 over here, that is just root of I1 I2, right. So, when you add these two, you get a 2 cos theta term, because the sine terms are cancelling each other. So, you have I1 plus I2 plus 2 root I1 I2 cos of phi 1 minus phi 2, okay. So, if I1 equals to I2, let us say is equal to I naught, then what do you get? I is going to be given by 2 times I naught multiplied by 1 plus cos of delta phi, right. So, that is in effect the response that you would see as a function of delta phi, okay. I will just leave you with this thought. Essentially, if you plot this I as a function of delta phi, then what you get is it basically goes through this sinusoidal function. When delta phi is 0, then this corresponds to the maximum, that corresponds to 2 times I naught, and then it is going to become a 0 at some point, go to a maximum, go to a 0 at some point, and so on. Where does it go to 0? I becomes 0 when delta phi equals to pi, right. And similarly, when delta phi equals to 2 pi, it will go to the maximum, and 3 pi it will go to minimum, and so on. So, what does that tell you? These are representative of constructive interference, and these points are representative of destructive interference. So, constructive interference happens, well, let us first finish destructive interference. Destructive interference happens when delta phi equals to odd integral multiples of pi, right, and constructive interference happens when delta phi equals to even integral multiples of pi. Okay. So, that is of course a lot of you know that intuitively, but if you go through the wave picture, you can show this. But the idea here and the idea that we are going to propagate forward is that to check this constructive and destructive interference criteria, you do not have to model that entire wave, okay. You just model the propagation phase that it accumulates, and you just compare the phase between the light beams that are coming together, okay. And based on that you can actually see constructive and destructive interference. And just working backwards, it all started with saying that light has this, when light approaches features whose sizes are comparable to the wavelength of that light, right, then it undergoes, it actually exhibits wave phenomena, which means that it undergoes this diffraction, it actually bends around these apertures, and that can give you this sort of things where once you consider them as secondary wavelets, those wavelets can come together and can interfere with each other, and it can give you constructive and destructive interference. Okay. For those of you that are taking this online course, we will have a demo of this experiment which looks at diffraction of light, and using the property of diffraction of light, how to measure certain feature sizes. Okay. So, that is what we are going to see, and moving forward, going towards next week, we are going to look at this in little more detail, and we are going to look at something else that is very important, which I have not touched much here, that is the property of the light source. So, you start defining that for all this to happen the way it is projected, you need to have a coherent light source. So, then what is the meaning of coherence? How do you quantify coherence? Those are the things that we are going to see in the upcoming week. Okay. So, let us stop at this point. Thank you.